The main goal of section 7.3 day 1 is really to be able to solve systems of equations using what we're going to call Gaussian elimination. And Gaussian elimination involves what we call the three elementary row operations. Three possibilities. We're going to use these at some point or another throughout the process. We won't always use every one in every problem, but number one is to interchange two equations, meaning that if I've got two equations, I can flip them around. If I had one in row 1 and one in row 2, I could just simply change their positions. Second possibility is to multiply one of the equations by a non-zero constant. That means I could multiply it by 2, or I could even divide by 2. I can, as long as I do the same thing to the entire equation, then it's still the same equation. That's just a concept that we've known about for a really long time. Third, and most important as far as row operations, is to add a multiple of one equation to another. One thing I really need to emphasize in this part is that we're only going to replace one equation at a time. If you replace both equations, then we would have the exact same equation on both, and it would, we would eliminate some information that we need in the problem. So let's get right to the example, and you'll see hopefully what each one of these means throughout the process. Here is that example. We are going to solve this system of equations using the elementary row operations, and we have, I think, a specific path that we need to take in this one. So I won't always tell you to do it my way, but in this case I really think you're going to need to do that. Number one is we're going to eliminate, because this is basically elimination in all this, is we're going to eliminate the lower x values. In this case we've got negative x, we've got 4x. We want to get rid of those first. Once we do that, we're going to eliminate the lower y value, the lower y variable. That's just going to be this one right here in a 3 by 3. Finally, like our last example, we are going to do back substitution to figure out what is the final answer to all of this. So first things first, we are going to get rid of one of these. I think the easiest one to see is the negative x. Now with elimination, with our method there, we can, if we add these two together, we know that that's just going to cancel out and we get a new equation. So I'm going to add these two together, and what that means is that x minus x, those just cancel. Y plus 3y is going to be 4y. Z plus 2z is going to be 3z, and then that's equal to 2 plus 8, 10. So that's going to be our new equation. Now we're going to replace one of these. I would leave the top row as is and replace equation 2. So what that means here is we're going to add row 1 and row 2 together and make a new row 2. A way to shorthand this is to say R1 plus R2 goes to R2. And that's going to make a new system that you see right there. So that's our new version of the system, and we're going to go from that one. Next, trying to eliminate this 4x. So what's coming up is exactly the same thing. Here is this. And we're going to try to eliminate that 4x now. So the 4x, let's mix it again with this one up here, because this one's really easy to manipulate. If we take and multiply this entire equation by negative 4, we're going to get negative 4x and 4x, and then those are going to cancel out. So I'm just going to bring this one to the side here. And so bring it to the side, we get negative 4x minus 4y minus 4z equals negative 8. Then we're going to leave this one as is, just bring that over to the side to add them together. 4x plus y, there aren't any z's in there, and then equal to 4. We add those two together. 4x's cancel, negative 4y plus y is negative 3y. We're going to bring the negative 4z down, and then negative 8 plus 4 is negative 4. So we are going to take this, we're going to add, like we just did, add negative 4 of row 1 to row 3, and then make a new row 3. So this is going to be going into row 3. Shorthand for this again would be negative 4r1 plus r3 is going to R3. You're going to see me use this shorthand more often in the coming examples. If we do that, our new system is going to look like this. So we're at a point where we have eliminated the x's, and now we've got to go for this lower y. But this next step, I just want to show you something that is a possibility. This is kind of an optional step, but I just want to show you that this is okay to do at this point. We've got this system. I can, at any point that I want to, flip the rows. Now, it's not entirely necessary in this case, but I'm going to just switch R2 and R3 to show you that it's okay. If we do that, you'll notice I've just flipped the two around, and that's one possible step. In some cases, it will actually be it'll actually be productive. In this case, it's not all that productive. But we're going to go with that. We're going to finish it out with that version of it. So here is that version. Now that we have this, we're going to try to pick off this y down here. In order to get opposites on the y's, we need to have 12s. And so I'm going to multiply this one by 4, and I'm going to multiply this one by 3. Bringing that off to the side, we're going to add these two equations together. So we've got negative 12y minus 16z equals negative 16. And then we have 12y, for this other equation, 12y plus 9z equals 30. Okay, we add those together. The y's cancel. We get negative 7z equals 14. That is going to go in place of our row 3. So that's going to be our new row 3. If we're going to if we're going to denote that, here is our row operation. We have 4R2 plus R3 is the new R3. So once we do that, we get down to this as our new system. All right, now you might notice where we're at. We are at a place where we're almost done with this problem. We can, at this point, do some back substitution. What we have now is what's considered triangular form. And if it's in triangular form, we can figure out what z is, keep going back through the problem. So with this last example here, this one is just going to be z equals negative 2, because we can divide the whole equation by negative 7. Okay, so we've got one of those variables. And then, like before, we just go back through, plug it in to this equation. If we plug in negative 2 for z, that's going to give us y equal to 4. And then if we go back and plug y and z into the original equation, that's going to eventually find that x is equal to 0. And so now we've got all three of our values. We can state our solution in an ordered triple x, y, z. And that is how you solve a system by elementary row operations.